What if I told you that inside a single droplet of water, we could store every single movie ever made, every book ever written, and every piece of data humanity has generated since the dawn of time? It sounds like science fiction, but it is a physical, biological reality. Right now, humanity is generating data at an astronomical rate. Every photo we upload, every video we stream, and every AI model we train generates millions of terabytes of data daily. To keep up, we are building massive warehouses filled with magnetic tapes and silicon hard drives. These facilities take up thousands of acres of land, consume vast amounts of electricity, and rely on rare physical minerals that are incredibly difficult to extract. Worse, our current storage media is incredibly fragile. A standard hard drive or solid state drive only lasts about 3 to 5 years before it starts to degrade. Even the industrial magnetic tape used by archives has to be physically copied and replaced every decade. We are silently running out of space, energy, and materials to store our collective digital memory. Hi guys, I'm Arya, and today we are going to discuss a very interesting topic. We are going to explore how biology solved our storage crisis billions of years ago. We are going to break down the science of DNA data structure, how it works, how we write binary into biology, and what it means for preserving human history. To understand how we can store data in biology, we have to look at the striking similarity between computer programming and genetics. A computer stores data using a binary code, a language of two states, zeros and ones. But nature stores the blueprint of all living things using a quaternary code, a language of four chemical bases, adenine, thymine, cytosine, and guanine. We represent them as A, T, C, and G. DNA is quite literally nature's original operating system. To store a digital file like a video or an ebook inside DNA, scientists use a straightforward translation process. First, a computer takes the digital binary file of zeros and ones and translates it into the biological alphabet. For example, a sequence like 00 becomes A, 01 becomes C, 10 becomes G, and 11 becomes T. Once the binary is mapped into the genetic alphabet, scientists use specialized chemical synthesis machines to physically manufacture synthetic DNA strands containing that exact molecular sequence. Important thing to be noted is this isn't living biological DNA like the genes inside our body. It is completely synthetic, inert, dry DNA. It doesn't need food and it has no biological function other than to act as a physical storage medium. To read the data back, we use DNA sequencing, the exact same technology used by medical labs to sequence genomes. Sequencer reads the molecular bases of the synthetic strand, translates the A, T, C, and G sequence back into zeros and ones, and reconstructs the original digital file with perfect fidelity. But the sheer density of DNA storage is what truly boggles the mind. In a traditional hardware, data is written on a flat, two-dimensional surface. But DNA is a three-dimensional molecule. It can pack information incredibly tightly. A single gram of dry DNA can theoretically store up to 215 petabytes of data. This is over 200 million gigabytes. Put that into perspective, you could store the entire internet inside a container no larger than a standard shoebox. And the longevity of DNA is unmatched. If you keep synthetic DNA dry, cold, and dark, it can survive intact for thousands of years. Scientists have successfully extracted and sequenced DNA from the bones of woolly mammoths that lived over 1 million years ago. Imagine if we could write our historical documents, our art, and our scientific discoveries into a physical medium that could survive 1,000 years without needing a single software update, a power source, or maintenance. Our digital archives would be virtually permanent. Of course, like any emerging technology, we are still navigating physical bottlenecks. Currently, writing DNA is slow and incredibly expensive. It is far too slow for you to use DNA to store your photos in real time or load a video instantly. But as synthetic biology accelerates, engineers are building new solid-state silicon chips that can write DNA thousands of times faster and at a fraction of the cost. And in the near term, DNA storage isn't meant to replace your phone's local hard drive. It is designed for cold storage, the massive archival data that companies and governments need to preserve safely for decades or centuries but don't need to access every second. When I reflect on this technology, I find it incredibly beautiful. For the last century, we have built our digital world entirely out of metals, silicon, and plastics. We have treated technology as something distinct from the biological world. DNA storage shows us a different path. It shows us a future where our most complex digital structures would be stored inside the very molecules of life itself. It reminds us that biology is the most sophisticated technology on Earth, and we are just beginning to learn how to write inside its margins. I'm so grateful to have you here on Arya Nova with me, and do let me know in the comments whether you would trust biology to preserve our human history. I'm Arya, and I'll see you in our next deep dive.